Okay, section 4.4 starts on page 45 of your course notes, and we are continuing on with derivatives. And this section is about derivatives of exponential functions. So if you follow along in your course notes, it says if y equals a to the x, so x is the exponent, then the derivative of y, if we derive it using the limit as h approaches 0, so we would have the limit of a to the x plus h minus a to the x, right? So you can go back to your limit laws, and we simplify it, we will end up with a to the x times natural log of the base. So the derivative of y equals a to the x is a to the x times natural log of the base. Now, you would also have to apply the chain rule. If your exponent is not just x, you would also have to multiply by the derivative of the exponent. So if this is the derivative of the outer function, then you would have to apply the chain rule as well. So example A says if y equals 5 to the x, then find the derivative. So our law says, or our observation up above shows that we would have the exponential function exactly as it's written times the natural log of the base. No more work to do than that. And the second example, now we have a product. So we have x squared times 5 to the x. So we would do derivative of x squared is 2x times the second function exactly as it is, plus the first function times the derivative of the second function. And we just did that above. So derivative of 5 to the x is 5 to the x times natural log of 5. Now generally we would take out our multiplication symbols to simplify it. This looks like an exponent right here, but it is not. So let me fix that real quick. Natural log of a regular old 5. Okay, so it says if a equals e, e is Euler's number, okay, in your calculator, then y equals e to the x. So the derivative is e to the x natural log of e. Now natural log of e is just 1. You can review your algebra if you want, but natural log is equal to the log base e. So if the base, so if we're taking natural log of e, the base and the number we're taking the log of are the same, so this is equal to 1. So if we're taking the derivative of e to the x, we simply get e to the x. We saw the derivative, if y equals e to the x, then the derivative is just e to the x. All right, next example, get a little bit more involved. If y equals e to the x times 3x plus z, we want to find the derivative. So again, we're going to use the product rule. So derivative of our first term. Now, we just saw that that would be just e to the x. But if we apply our rule as usual, we have the exponential function exactly as it's written times natural log of the base. So derivative of the first times the second, which would be 3x plus 2, plus the first times derivative of the second term. So derivative of 3x plus 2 is simply 3. And if we simplify this, again, natural log of e is just 1. So we would have e to the x times 3x plus 2 plus 3e to the x. Okay, part B. Now we want to apply the quotient rule. So we have a division. So as we do this, we want to take derivative of the numerator times the denominator. So the derivative of the numerator is just e to the x times the denominator minus the numerator times derivative of the denominator. Now notice both of these, when we take derivative of the denominator, our plus 1 would be gone. Okay, so we have, again, derivative of the numerator is just e to the x. Okay, so on the previous, so when I find the derivative of the numerator, we just get e to the x. Now, when I find the derivative of the denominator, we get e to the x, right? Again, the derivative of 1 is just 0, times the numerator, which again is e to the x. So it looks very repetitive, a little bit confusing. Okay, so then we divide by the denominator squared. Okay, so we can simplify this a little bit. Notice in this first term, if we distribute this e to the x to each of these terms, we will have e to the x times e to the x, which is e to the 2x. And that will cancel with this when we distribute it. Okay, so e to the x times e to the x is e to the 2x, and then plus e to the x, right? We distribute it to the second term, minus e to the 2x over e to the x plus 1 squared. So these terms will cancel out, and we end up with e to the x divided by e to the x plus 1 quantity squared. And that would be as simplified as we can go. Okay, now there's a note here on this page that says, remember the chain rule for composite functions. So for example, if y equals e to the x squared, then when we take the derivative, we must also apply the chain rule and take the derivative of the exponent. So when we find the derivative, we would have the derivative of the outside function. So we would have it exactly as it's written, take natural log of the base, but we already know that's 1, okay? But for learning purposes, I'm gonna write it. And then we would add, and then we would multiply by derivative of the exponent. So the derivative of just the x squared, which is 2x. So when we simplify this, we have 2x e to the x squared. Again, natural log of e is 1. All right, so now we're on the next page, page 46 of your notes. And we have a bunch of examples of applying this. So part A, same thing. We want to take derivative of this. So we take the derivative of it, the outside function, which is just e to the negative 2x times natural log of e, which is 1, and then derivative of the exponent, which is a negative 2. Derivative of negative 2x is negative 2. And we can simplify it. Pretty straightforward. Part B is similar, but notice we have this negative 8 in front. Okay, so we're going to leave the negative 8 out front. So we would have negative 8 e to the 3x times natural log of the base, which is 1, times derivative of the exponent, which is 3. So when we simplify it, we get negative 24 e to the 3x. Part C is just like remember the composite function thing right above it, however, or on the previous page. However, we have a negative 2x. So again, derivative of the outer function would be just the function as it's written, e to the negative x squared times natural log of the base, which is 1, times derivative of the exponent would be negative 2x. Derivative of negative x squared, the exponent comes in front, so we have negative 2x, decrease the exponent by 1, so our new exponent is simply 1. Okay, now we have y equals x times e to the x. So in this case, we do need to apply the product rule, right? So we have x times e to the x. So we take the first term times derivative of the second. Derivative of e to the x is just e to the x, plus the first term, or plus the second term times derivative of the first. So the derivative of x is just 1. Okay. Now, sometimes it's helpful to factor out the e to the x. So if we factor out this common term from each of these from this binomial, we would end up with x plus 1. That's not required, but sometimes you'll be able to cancel that with the denominator. So I just want to throw that out there. Okay. Another example. Now we have the quotient rule, right? So when we find this derivative, we will take the denominator times derivative of the numerator, so e to the x. Now we'll have a minus e to the negative x. But when we take the derivative of e to the negative x, the exponent is negative. So we will have it multiplied by a -1, which would make this positive. So again, when we take the derivative of negative e to the negative x, we get it exactly as it's written, times derivative of the exponent, which is just -1. So that would flip the sign. Okay. And then, so that's denominator times derivative of the numerator plus the numerator times derivative of the denominator, which is just 1. So we don't need to write it. Oh, not plus though. Why did I do that? Right? Our quotient rule, we should have a negative right there. So make sure we put parentheses around it so we don't mess up our signs. So denominator times derivative of the numerator minus numerator times derivative of the denominator divided by denominator squared. Okay. So it doesn't look like we'll be able to simplify this at all, but our first terms we could distribute the x just to see if we can cancel anything, distribute our negative, and it doesn't look like anything is going to let us cancel, so we will just stop there. Okay, an application problem. The sales of a new product is given by the function s of t equals 100 minus 90 e to the -0.3t, where t represents time in years. Find the rate of change of sales after 5 years. Okay. So we want to, whenever it says rate of change, this means derivative, okay? The rate of change is always going to be the derivative. So it says t represents time in years, so if we take the derivative of this, this would be the change of sales over time. So again, the derivative would be the change in sales over time. Okay, so when we take the derivative of this, the derivative of 100 is 0. The derivative of -90e to the -0.3t, well, we would write it exactly as it's written, and then we would take the derivative of the exponent, the chain rule. So now, remember when we take the derivative of an exponential function, we write it as it is, take natural log of the base, but natural log of e is just 1, so I didn't write it, times derivative of the inner function. So the derivative of the exponent is -0.3. Okay, now you can use your calculator. 90 times -0.3 is 27. So we have 27e to the -0.3t. So this is the change in sales over a given amount of time. Now the question is asking, we'll find the rate of change after 5 years. So the rate of change, if we plug in 5, we're just going to have to use a calculator, and we get approximately 6.025 units. It says units, right? It doesn't say. So actually that's probably not units. I don't know why I have that in my notes. Yeah, so 6.025, about 6.